If I had $1 for every time I had to restart this video because a truck that just sped up the hill next to the house decided to go downhill. Good morning, everybody. This is Sean Downs, Sean for Science with the Pasayten Institute, and today is another great morning to discuss mathematics. Specifically, we're going to be talking about the representation theory of SL2R. Good morning, everybody. This is Sean Downs, Sean for Science with the Pasayten Institute, and today is another great morning to discuss mathematics. Specifically, we're going to be talking about the representation theory of SL2R. Now, I have been trying to make this video for days, if not weeks, so I'm excited to give it another go. So, without further ado, let's get started. We have been studying subgroups of SL2C for quite some time and have invested a lot of time and energy into discussing representations of arguably the most famous of those subgroups, SU2. A lot of the work that we did with SU2 is going to pay off today because we'll be able to mostly just repeat the analysis for the case of SL2R. SL2R's representation theory is a little bit more intricate and it's a little bit more nuanced, but it's also a lot richer. So hopefully it'll at least be more interesting to you if you haven't seen this stuff already. Recall that the Lie algebra of SL2R, which is the same as the Lie algebra of Sp2R, which is the same as the Lie algebra of SU1, looks a lot like the Lie algebra of SU2 with one important difference. One important minus sign difference. That minus sign in the commutation relations is going to have a huge impact in the structure of the representation theory. But before we discuss that, let's discuss the origin of where that minus sign comes from. So recall that SL2C is basically the complex span of the three physicist sigma matrices, and SU2 was the real span of those matrices. Now, for some element G in SU2, G amounted to a rotation of the quaternions that effectively left the hyperplane defined by the kind of the real quaternions fixed under those rotations. So in the same spirit, we can try to fix other hyperplanes of the quaternions by choosing other sigma matrices to be left invariant. So for the specific case of SL2R, we can consider the case where these parameters, say alpha, beta, and gamma, go to alpha, I beta, and I gamma. In this spirit, we can define a basis for the representation of SL2R for the Lie algebra by choosing, say, A sub 0 to be sigma 1 over 2, and A plus or minus to be I times the quantity of sigma 2 plus or minus I sigma 3. So very similar to the SU2 case. After a slight change of basis, this amounts to a Lie algebra map from the Lie algebra of SU2 to the Lie algebra of SL2R, given by, right, so J3 and A0 are the same, and A plus or minus are basically factors of I times J plus or minus. And those two factors of I correspond to the minus sign that you observed in our commutation relations for SL2R. The quadratic Casimir Q of SU2 can be similarly mapped to something we'll call C here. And keeping in mind the existence of those two factors of I, we get, which again kind of differs from the SU2 case by a factor of -1. Note that we choose a convention which effectively multiplies the operator C relative to the operator Q by an entire minus sign. Okay, so let's talk about the unitary representations of SL2R. So again, we're going to follow the so-called Bargmann's logic that we applied to the study of unitary representations of SU2 to this particular case. For more details, please check out that video. I'll link it in the show notes. So we're going to go kind of quick here. So let little v be some member of some irreducible representation of SL2R. We don't really care which one. All that we're really interested in is the vector v prime, which is given by a plus acting on v. Unitarity of the representation demands that the inner product of v prime with itself be positive definite. Because the original operators are self-conjugate, or more to the point, the a plus or minus are kind of related by conjugation, we have within the inner product, which once again we can replace that with the appropriate terms coming from the definition of the Casimir operator. This, of course, is just an eigenvalue equation, so really what we have is a constraint on the eigenvalues of the representation with respect to the operators C and A0. So this is now effectively an inequality on the space of possible eigenvalues for the space of possible unitary representations. That is, q plus m squared minus m must be greater than or equal to 0. Note the overall minus sign relative to the similar case for SU2. Of course, we can do the same thing with the different representation of the Casimir. That is to say, we can do the same thing starting with the lowering operator a minus and find an equivalent inequality, which basically gives us the same two parabolas that we saw for the case of studying unitary irreducible representations of SU2. So indeed, we have the same plane of eigenvalues. We have exactly the same two parabolas, although there's an overall minus sign from our choice of convention. So in other words, the unitary region is now below the parabolas, which is why we flip the parabolas upside down, just to have large positive numbers. That's really the only reason. But notice the following thing. Because the unitary region is below the parabolas, that wedge region that we discussed for SU2 is no longer part of the unitary representations, which is why the unitary representations of SL2 are considerably more intricate and complicated. In particular, note that the allowed values of the eigenvalues in the unitary region is not even a convex subset of the plane. Like there's this little concave region in there, which is going to make things especially interesting and richer in structure. So in order to catalog all of the unitary irreducible representations of SU2, we're going to need a few results. Specifically, we're going to need 3. So let's go through them. Claim 1, that all irreducible representations of SL2R have a fixed value of q, although q does not fix the representation completely. 2, if the point, say m prime q prime, in the plane of eigenvalues belongs to a given irreducible representation, then either m prime is the maximum value of m, or m prime plus 1 q prime also belongs to that same irreducible representation. And similarly, if the point m prime q prime in the plane of eigenvalues belongs to a given irreducible representation, then either the point m prime is a minimum value for m, or m prime minus 1 q prime is also a member of the irreducible representation. Hopefully this is vaguely familiar to you from our discussion of SU2. So, proof. 1 follows from the fact that the Casimir commutes with A0, so that's easy. To see 2, let V belong to an irreducible representation with A0 eigenvalue m. Then a simple application of the commutation relations gives us the fact that A0 with A plus on V equals m plus 1 A plus on V, or A plus on V is equal to 0. Now, if A plus on V is equal to 0, then A plus on, A plus to the mth power on V, A plus, to any power on V is also going to be given by 0. So either A plus annihilates V, so m is a maximum value in the irreducible representation, or we hop over to the m plus 1 eigenvalue. 3 follows from a similar line of argumentation involving A minus. So just a quick remark here, the cases where A plus or minus on V equals 0, where they're the maxima or the minima in the irreducible representation, are precisely the cases where that representation lands on the parabola itself, just like we saw with SU2. Okay, so let's go ahead now and catalog the irreducible unitary representations of SL2R. So the plane of eigenvalues m and q will be our guide to this catalog, and to that end, note that the unitary constraints divide the plane into kind of the following relevant eigenvalue sets. So first, the case where q is less than 0. Second, the case where q is between 0 and 1/4. And third and finally, the case where q is above 1/4. Let's now consider each region in turn. So starting with the negative q region, so we have another claim today. For each q less than 0, there are precisely 2 irreducible representations, indexed by plus or minus 1. We will call them d plus or minus q. For negative values of q, the region of non-unitary eigenvalues is wide, much wider than the unit interval, which means that action by a plus or minus cannot hop over that particular region. So either you're on the left side of that region or the right side of that region. Now, these are the same arguments that led us to the discussions of SU2. If you're just a little bit off from the parabola in the unitary region, action of a minus or a plus will pop you into the forbidden region, so that's not allowed. So really, the only representations that are allowed are those that end on the bounding parabolas themselves. So in other words, we have kind of the complement of the types of representations we saw with SU2. That is to say, we start with a maximum or minimum value, those on the parabolas themselves, and then we consider all actions of a plus that take us out in the positive direction, or a minus, which take us out in the negative direction. The positive side gives us one of our representations, and the negative side gives us the other of our representations. There's one for each value of Q, and so these are the discrete series of representations of SL2R. We're going to skip over that kind of concave intermediate region for a bit and go straight to discussing Q greater than 1/4. So here's our third claim for today. For each Q greater than 1/4, and M in the semi-open interval from 1/2 to -1/2, there is an irreducible representation of SL2R, which we'll call, C of Q and M. Proof. Okay, so fix a value of Q greater than 1/4. Without any restrictions on unitarity, there is no maximum or minimum values of M. The forbidden region is nowhere near this area. Hopping over with A plus or A minus, you can go off in either direction unimpeded. Thus, any one-dimensional lattice in the plane with a fixed value of Q is a valid representation of SL2R. So the question then just reduces to discussing, well, what are the distinct one-dimensional lattices in the plane for fixed values of Q? And we can uniquely index those by that semi-closed interval from -1/2 to +1/2. And so that, boom, and so we're done. These, according to Bargmann, are the so-called continuous representations of SL2R. See, it's already much richer and much more complex. Good. Okay, so now let's get into the dirty business of discussing what is happening between the region of Q equal to 0 and Q equal to 1/4. For each value of Q between 0 and 1/4, there are 4 distinct, discrete, unitary, irreducible representations of SL2R that are indexed by the values of Q and M. These are not the only ones. There will also be continuous representations as well, but let's do the discrete ones first. So for each Q, the forbidden region now has a length that's less than the unit interval, which means that the actions of A plus or A minus can actually hop over that forbidden region. So related to this fact, for a fixed Q, there are 4 points on the bounding parabolas of the unitary regions, 2 with positive values and 2 with negative values. These 4 points will act as either maxima or minima for their own discrete representations. For the 2 cases where M is greater than 0, the distance between them on the 2 parabolas is less than the unit interval, which means that they must belong to distinct, that is, different representations of SL2R. In both cases, the relevant eigenvalues of A0 correspond to minimum values of M in both of the representations. Amusingly, note that these representations can actually leapfrog over each other as they go out to infinity. They're, again, semi-infinite discrete representations. Thus, for a fixed value of Q, we have dQ of M plus given by, and of course, similar arguments for negative values of M for the same value of Q give us the other kind of d of Q M with minus. Note that, as with the Q less than 0 case, the symmetry kind of relates the positive and negative values of M for a given factor plus or minus 1. So finally, it's worth pointing out here that there are also continuous representations present in this particular region of Q, although their values of M are restricted. So following claim 3 that we had for the discussion of, positive or, for large values of Q, we have continuous representations given by, with the added restriction that no points should be allowed to hop or land into the non-unitary region of parameter space. Okay, so a quick remark here. The case of Q equals to 0 has 3 irreducible representations. One at the origin, which is the trivial representation that was also a representation of SU2, if you recall. But now there's also 2 representations with M equals to plus or minus 1 respectively. And those are just similarly defined as discrete representations that go out to minus infinity or plus infinity. For the case that Q is equal to 1/4, we see that just below it there would be 4 representations, and just above it we'd have a continuum of representations. So actually what happens is those 2 distinct representations around each local extrema of the parabolas kind of coincide. And so we actually have 2 irreducible, discrete, unitary representations of SL2R for Q equals to 1/4. It's worth pointing out here that Bargmann's original classification of these representations involved a different parameterization where he chose like Q equal to K times 1 minus K for, just bookkeeping reasons. Okay, so that's the basic landscape of unitary irreducible representations of SL2R, which is enough for now. I realize that's probably not very helpful without some concrete constructions. So this video's been long enough. We will discuss concrete constructions of SL2R representations in a later video. Talk to you series. Have a great day. That kind of concave intermediate region for a bit and go straight to discussing q greater than 1/4. So here's our third claim for today. For each q greater than 1/4 and m in the semi-open interval from 1/2 to -1/2, there is an irreducible representation of SL2R, which we'll call, C of q and m. Proof. Okay, so fix a value of q greater than 1/4. Without any restrictions on unitarity, there is no maximum. The